All right, folks, this is constant acceleration formulas, part two, fire drill formula. So far we've done position function and average velocity being the slope of the secant line. All right, warm up review question. The solution of the quadratic position function, solving for time, will sometimes yield two real answers. What is the significance of the time that you get when you average these two times? So since the parabola is symmetric, so again, this isn't the shape of the path. This is that the object is going up and then back down. Even though I included this picture, I probably shouldn't have. Anyway, if you have two times that the water shot straight up and straight down is at a certain location, T1 and T2, by the symmetry of the beautiful parabola, you would get the time at the peak. And that's a completely legit way to find it because you're saying that you understand that there's symmetry and physicists love symmetry. Okay. Now, in terms of the fire drill formula, if at Murray, instead of lining up by alphabetical, we lined up by height, and we're like, hey, something funky's going on with the admissions office because every person is exactly 1 centimeter taller than the person to their left, let's say, whatever. All right, so if the altitude of every single person in this picture were exactly whatever, some amount greater than the person below them, how could we easily find the average height of all 8 people? So pretend like I drew 8, and we have person A and we have person B. And how could we find the average height? All right, hope you got that right. You could average A and B. You could average C and D. You could average E and F. Any two people that are equal distance apart would yield the average because the average in this case will be the person in the middle. Okay, I know I said 8, so there's no person in the middle. If there's an even number, it would be the average of the final two people. So any two people that are symmetrically distributed away from the ends are going to yield the average height. But that's only true if there's this bizarre occurrence that they are growing at a uniform rate. Okay, so I love that visual. It'll help you remember it. That's why I call this the fire drill formula. If you go to college and take this physics class, don't say, let's use the fire drill formula, and nobody's going to know what you're talking about. But if the velocity is going from 0 meters per second to 30 meters per second at a uniform rate, the average speed is 15 meters per second. Okay, in case we haven't talked about this, bar means average. You're going to take the speed at the beginning of the time interval, V naught, and the speed at some later time. You're going to add them up and you're going to divide by 2. Okay, so like super handy. What that means is if I went from 0 to 30 faster and faster and faster, right? I have some times when I'm going slower, but some times that I'm going faster. That is equal to, in terms of gaining ground, if I traveled at this orange constant rate of 15. That's what it means, that I could go slow and then fast and get to my favorite wherever you're going. Or I could decide I'm going to go at a constant speed of 15 for the same time and you'll get to the same place. Okay. So you will get this formula on the test. I hope that it makes fundamental sense to you. Okay, so again, this formula only works if your speedometer dial is increasing or decreasing. If you went from, 60 to 30 at a uniform rate, the average would be 60 plus 30 over 2 or 45 meters per second, right? It works either way. And this is simply finding the midpoint of the velocity versus time function. Okay, so hand in hand with that fire drill formula is what I call, again, I made up this equation name, don't know, don't care about acceleration, because you notice that there is no acceleration in this equation. So you can use the position function where this is V naught and you deal with the acceleration. But let's say you just know the car went from 0 to 60 at a uniform rate. You could it in 5 seconds. You could find the acceleration, but if you don't care what the acceleration is, if you just want to know, hey, how far did I travel, then your final location is your head start plus your average velocity times time. And then super quickly, if we solve this for V naught, you can see that, and assume that we started the clock at t equals 0. This formula is just the definition of average velocity that was, whatever, 2 videos ago, delta x over t, slope of the secant line. It's just rewritten, but hopefully this makes sense. How far I get is basically that your average velocity is telling you how, on average, how quickly you are gaining ground. One super quick note, I should be more careful. This isn't really t like the input time that we did for the position function. This is really the time interval delta t over which you are calculating the average velocity. We're just going to be lazy and just start the clock in that time interval at 0. Okay, so a look at that. We'll do an example problem. A car goes from 0 to 60 in 3 seconds. Calculate the distance traveled by the car in this time. So if you try to set up the position function, you would realize you're missing information. You know V final instead of A. So again, you could find the acceleration and then use your position function. That's not wrong. I would count that on a test, but we're practicing the fire drill formula. So first thing we want to do is calculate the average velocity. So please do that. Pause the video and do that. So again, standard documentation is write the equation, substitute your values. Sorry, technically 0 is V naught. So that makes more sense. V naught plus V, doesn't matter. 0 plus 60, you might want to put units in here just because it's so simple. Over 2 means on average the car was going 30 meters per second. Okay, and then calculate the distance traveled. Unfortunately, often in problems, they don't specifically say the car started at t, at location 0. So you can assume that is 0. They didn't state it. Plus 30 meters per second times 3 seconds, or 90 meters. Okay, I'm going to show you. You can kind of, you can't fast forward, but you can zip through this. You could say, you know what, I'm going to calculate the acceleration. Oops, there's no bar there. I'm going to calculate the acceleration. That's my change in velocity over time. That's the fundamental definition of acceleration. I went from 0 to 60 in 3 seconds. So I am gaining speed at a whopping 20 meters per second squared. So that's how quickly I'm gaining speed, and now I can use my position function to figure out how far I went. So again, didn't have a head start because otherwise I need to be told that. My V naught is 0. So there's a lot of V's hanging out here, so be careful. It's not 60, it's not 20. It's 0 times t plus your acceleration, which is 20, times your time, which is 3 squared over 2. So 20 over 2 is 10, times 9 is, 90 meters. Okay, so again, one of the nice things about physics is there are sometimes ways to check for self-consistency. And if you had time, if you're turning in a problem set, in college and you want to make sure you're right, you can do this more than one way and you can be like, oh, awesome, I got the same answer using 2 different methods. All right, so hopefully that all makes sense. Thank you for listening, and I will see you in class.